trying to use neon data to understand in-stream versus watershed contributions to gas flux. And NEON provides an exciting opportunity to do this because they have 28 monitoring sites distributed across the US with paraterrestrial and aquatic data along with groundwater data. So right now they've got about 5 years of continuous data collection, all using the same methods, which lets us make these broad scale comparisons. I'll just note before I go into this is done by a massive team, so a lot of Duke and Fort Collins collaborators. And if you're ever interested in a really well done public data portal where we're putting up a lot of this, take a look at the MacroSheds website. Okay, so the way that we're doing this with NEON data is we are combining study of gas concentrations collected about 28 times per year with an understanding of stream hydrology using various data sets like dissolved oxygen and discharge data, analyzing watershed attributes, and then also groundwater contributions using isotopes and water levels. And our goal is to combine all of these data into multivariate models, which we can use to continuously predict greenhouse gas flux across those NEON sites and understand various drivers at this broad scale. In our initial analyses, we've looked at the concentrations of those 3 greenhouse gases across the 28 sites. So on the top panel here, I'm showing carbon dioxide. On the bottom panel, methane in the orangish color, and nitrous oxide ordered by increasing CO2 concentrations. The site names are on here. The main point I want to make is there's quite a bit of variation across these NEON sites that we typically tend to think of rivers as well oxygenated, yet we're seeing fairly high methane concentrations, which tend to be produced with a lack of oxygen in some of these sites. And that these values are actually representative of the variation we see at global scales. So it's a good chance to study drivers. And taking a look at the drivers across these different sites, just an initial look, we've analyzed some of the watershed attributes. These sites are quite different, especially in terms of slope, although they tend to be about the same size, and temperature regimes especially. And starting to break down these different drivers, I'm showing here a correlation plot. So red indicates a strong positive correlation, down to the darker gray color shows stronger negative correlations. The greenhouse gases are shown on the bottom here with that greenish bracket. And I'm going to break down a few of these and just draw your attention through different parts of this. So the first thing I want to point out is this strong control coming from catchment slope or stream slope, which indicates physical controls on greenhouse gas processing. So basically, the steeper the stream, the more turbulent it is, the more likely that gases are going to flux out of the stream, and also the more likely that it's going to remain well oxygenated. Whereas here I've highlighted a variety of different drivers. So temperature has a positive correlation with both CO2 and methane, and then dissolved oxygen has a negative correlation with both gases, and CO2 and methane are tightly positively related. And what this indicates to us is the potential importance of biological controls. So again, we have in-stream processing that could be driven by this balance between photosynthesis and respiration, which can be affected by higher temperatures. And then also lower dissolved oxygen could indicate more respiration occurring, and also the potential for methane production. And so I'm going to bring this will make a little bit more sense when we start bringing it into Nuvo Creek. And so just highlighting this even more, the sites with the highest CO2 and methane concentrations tended to be our highest temperature, lower slope, lower dissolved oxygen sites. So you could think of these as sort of more stagnant, warmer streams. And these are a couple examples. I just pulled out 2 sites as examples, the Arickaree River in eastern Colorado and McDiffit Creek in Kansas, which are both these slower, low gradient, organic matter-rich streams, which tend to be depleted in dissolved oxygen, which is what you're seeing on the y-axis here, but also be very supersaturated in carbon dioxide. And by looking at these relationships, we can conclude that these sites have potential groundwater inputs or potential anaerobic metabolism, just based on that balance. These sites, I'll also just say, but I'm not going to show data here, are also the sites that tend to have the highest methane concentrations. And so we think that those streams where we're seeing the highest CO2 concentrations and some buildup of methane, those low gradient warmer sites, are quite similar actually to our North Carolina Piedmont streams. So this is a picture of New Hope Creek that you're seeing here. And one of the issues that we've seen with NEON data and the way that we study greenhouse gases in rivers in general is that we often take a point measurement and then assume it represents some length of stream. And so this is a picture of the NEON sampling scheme, which is often used in these stream greenhouse gas studies. The star is where greenhouse gas measurements are collected at every single sampling event. So it's 1 point representing half a kilometer to a kilometer each of stream. In the picture, in the background, that star is indicating where that measurement might be taken in New Hope Creek, so the closest thing to a run that we have in these low gradient streams. And it's just one type of habitat in the reach. So you can see the water looks like it's actually moving in the lower part of the picture. And in the upper part of the picture, it's really not clear if that's a stream or a pond, which is why we've been jokingly calling this the Piedmont Peapod hypothesis. And so we think that that point might not be representing what's actually happening in a given reach. And we're going back to this idea that the physical and biological controls on greenhouse gases vary with local geomorphology. And so we're going into our second part here. What we think is happening and what we're testing this summer is that greenhouse gases accumulate in those ponded sections, or our Ps. And then when they hit the riffles, those riffles basically act as a chimney with higher gas flux because of the turbulence. And so specifically studying drivers of greenhouse gas production in those ponds might be more fruitful for us to understand what's happening in these streams. So this is our postdoc, Nick Marzoff, leading this study. If you've ever been to Hollow Rock Nature Park, we're actually moving upwards from there, so it's at the downstream end of that picture there. And we're trying to understand longitudinal heterogeneity there by pairing pool and riffle sequences. So we're installing continuous methane and carbon dioxide sensors, mimicking some of the NEON approach, but taking more of a longitudinally explicit approach, and then trying to understand groundwater contributions by installing wells along this reach, and constantly measuring all these different drivers that could be biological controls on greenhouse gas production. So we're very excited. A team of UNC undergrads, Nick Marzoff, all came out and started installing wells last week. I think I'm running out of time here. So I will just say that as we start this, we're also going to be working on understanding greenhouse gas flux from the exposed parts of river channels. So you can see the exposed gravels in this picture here, which could be very strongly affected by how we manage hydrologic regimes. So for example, dam releases or releases from wastewater treatment plants, as well as additional channelization, and then eventually comparing with more urbanized watersheds such as that in Ellerby Creek. So with that, thank you very much for having me.